Good afternoon, guys. Today we are going to perform experiments called amplitude modulation. So, last class what we have performed was pulse amplitude modulation and amplitude modulation and frequency modulation. Okay. So today we are going to perform the experiment pulse amplitude modulation. So what are the main objective of this experiment? To understand the time domain and the frequency domain representation of the signal, okay, and to investigate the generation of PAM signal. Okay, so you can see here, this is the continuous time signal and these are the samples. So let me focus here for you. This is the time continuous and this is time discrete signal. So here we are going to just generate a discrete signal. Okay. So here you can see this is a time continuous signal S of t, which has a time period of 0 to t. Okay. So here you can see in the second part, okay, the spectrum part, there is a one sample of, okay, the spectrum, there is a one sample that is 1 by, which is coming at 1 by t. Okay, and wherein this is the time domain representation. Okay, this is a frequency domain representation, this is frequency domain representation, and from 0 to t for this square wave. So the spectrum is at 1 by t, 3 by t, 5 by t, 7 by t and 9 by t. So these are the odd multiples. You can see these are the odd multiples, so where you will get the spectrum. Okay, so let us start with the experiment. So for first thing, what is there in the conversion from analog to digital is sampling, quantization and the coding. This three part includes analog to the digital conversion. So for converting analog to digital, first step is sampling. Okay, we will do the sampling here, quantization and coding. Okay, so as you know, studied the sampling in the theory, so we will not concentrate on the sampling. Okay, already explained in the theory. So the second part is spectrum of PAM signal. So here you can focus. Let me focus here. So again here you can see this is FM. So here you can see this is SP of n. That means pulse. FP3, FP, F5, FP7, FP. Okay, this is FM. That is nothing but the message. This is pulse. Okay, this is for the pulse and this is for the message. And here you can find for the PAM. So this is first spectrum is the message. Whatever the message frequency you will get the message frequency FP. Okay, first FP you can find FP1 plus FP minus m, FP plus m and FP minus m, like same like a upper sideband and the lower sideband. Okay, 2 FP same way, FP plus 2 FM, FP minus 2 FM. Okay, 3 FP you will get FP plus 3 FM plus F3 minus 3 FM. Okay, similarly you can generate all the pulses of pulse amplitude spectrum. Similarly, so let us start with the experiment. So here we are just generating the pulse amplitude waveform. Okay, pulse amplitude waveform. Here we are generating pulse time domain representation of pulse amplitude waveform. Let us start the experiment. Let me make the same thing you can find here. Okay, so this is the time domain representation. Okay, this is a pulse. So you have a one spectrum at 1 by t. This is square wave. You have a spectrum at the odd multiples. Okay, so let us make this connection here. Okay, so how it is connected, you can see this is grounded and we are generating for 5 kilohertz. Okay, 5 kilohertz to the output. Okay, so we have connected this one. Okay, we'll connect this. Kilohertz we just connected to the 8 kilohertz and to the output y1. Okay, so let us set the parameters here. Open the oscilloscope by clicking the button. Okay, and set the time for division 5 microhertz and delay 0. So let us go to the function generator, sorry, oscilloscope, make it 500 kilo microhertz. Okay, and delay is 0. Okay, here you can see this is the pulse, generated pulse. Okay, this is generated pulse. You can take the amplitude here as how much it is, y1 9.4, sorry, 4.94, and here it is 0 millivolt. Okay, you can draw this as the first output here. Okay, you can write the bottom amplitude as 0 millivolt and top amplitude as 4.94. Okay, you can draw it here. Next part, now open the F50 module by clicking on this button. Let me close it. Open the F50 by clicking this. Okay, open the F50 and Fmax is 100 to set the resulting output. Record the spectrum. Okay, let us record the spectrum. So here you can see. So let me close it and make it how much? We'll make it 100 kilohertz as it is given in the procedure. Okay, just click it. So you will get the pulses. So as you have seen in the theoretical part, the first pulse will be at how much? 0 kilohertz. Okay, the next pulse will be at 8 kilohertz. Okay, it is multiple of 8. Okay, it is 0, 8, 8 3 is 24. Okay, so it will be multiple of 3, 8, 24, and again 8 multiplied by 5, it will be 40. Okay, just take these peaks, not the small ones. Okay, take these peaks. So FP, okay, this is FP, this is 3 FP, and this is 5 FP. Pulse frequency. What is the frequency we have given here? We have given the frequency 8 kilohertz here. Okay, this is pulse frequency. It is 8 kilohertz. So FP is how much here? 8 kilohertz. Okay, you can see here. You can see here it is 8 kilohertz. Okay, and 3 FP it is 24, and 5 FP is how much? 40. Okay, similarly you can just take this one also, the peak. Okay, just draw the first 3 peaks and write the 3 frequencies here. Okay, so first is 0, so you can write 0 here, you can write 8 here, you can write here 24, and you can write how much here? 40. Okay, just accordingly just write, comment it. Now the next part is generation of PAM signal. Okay, so let us see the circuit diagram for it. So how we connect it from 1 kilohertz. Okay, this is sine, and this is 3.4 kilohertz. Okay, so let us make the connection here. So here I have connected this. This is the circuit diagram. Okay, according to the circuit diagram, I have connected the circuit. Okay, so let us now follow the procedure. So open the oscilloscope, by clicking this button, set the time division to 100 microsecond. Okay, so open the oscilloscope. We close this. Again, open the oscilloscope. How much it is? 200 micro, and delay is, we click Y2 also here. Let me run this. Because we have now connected this 8 kilohertz. Okay, because without this you will not get any output. Okay, so let us go back to the oscilloscope. Open the oscilloscope. Okay, this is what your output looks like. Okay, this is called as a natural flat top sampling. Okay, you can see here. So each positive half pulse has how many pulses here? 1, 2, 3, 4. Okay, here also 1, 2, 3, 4. So that means in one cycle you will be getting 8 pulses. Okay, so here we complete second part. Okay, let's come to the next part. It is generation of PAM spectrum. Just write it here. Number of carrier pulses as 4. Okay, half in half wave. In half wave, the number of carrier pulses are 4. This is 1 kilohertz generated frequency. Okay, so this is 1 kilohertz per spectrum. Just I told you in the theory. Okay, this is FP minus FM, FP plus FM. Okay, so this will be FP, first pulse plus the generated sinusoidal frequency, and FP minus FM. Okay, so similarly this will be 3FP minus FM, 3FP plus FM. Okay, so here you can draw this here. So you can draw first 3 pulses, and you can so here you can draw first 3 pulses. Okay, here you can draw first 3 pulses, and you can write the frequency as 7, 1 kilohertz. Okay, 1 kilohertz, 7 kilohertz, and 9 kilohertz. Okay, so next part is aliasing. So next part is aliasing effect. So here is the circuit diagram. So let me close this for you, and let me check the circuit diagram from here. So just go to the next one. Okay, this is the circuit diagram. Let us connect the circuit diagram first. We have connected. You can verify here. Okay, so let us set the parameters according to the given procedure. It is FPP is 5 volt and V is equals to 2.5 volt and duty cycle is 50 seconds. Okay, so VPP is 5 and initial frequency is 10 kilohertz and duty cycle is 50%. Okay, so let us first click the square wave, and this is V is how much here? 2.5 and 50% duty cycle. Okay, so next open the oscilloscope and just set wiper division as let us make it as 200 micro. Click Y1 and Y2. Okay, both Y1 and Y2. So here you can see this is the aliasing frequency, aliasing effect. Okay, so this is actually your generated signal, and this is your alias effect. Okay, so just you can draw here. You can draw it here. Okay, so let us go to the next part. It is the circuit is same. Okay, now just open the spectrum analyzer. Open the spectrum analyzer and make it how much here? It is given as F max as 10 kilohertz only. Okay, just run it and take the corresponding frequency. Here you have 1 kilohertz. Okay, this is for sample 1 kilohertz. You can see here, and next sample is at 9 kilohertz, 8 kilohertz, 7 and 9. Okay, previously what we did it. Okay, 7 and 9. So just you can draw here 1, 7 and 9. Now make FP pulse frequency as 5 kilohertz, 2 kilohertz and 1.5 kilohertz. Okay, correspondingly you can draw all three values here and you can comment it. Okay, for 2 kilohertz just write the frequency whatever it is. So let us now change the pulse frequency to 5 kilohertz. Now let us change the pulse frequency to 5 kilohertz. So this one is the pulse frequency here. Frequency to 5 kilohertz, and here we can see the changes in the pulse.
After just changing the frequency from 5 kilohertz to kilohertz and 1.5 kilohertz, you can find this is the frequency. This is for the 2 kilohertz, and just you can see the frequency here, it is around 1.5. Okay, around 1.5 here, and here when we change the frequency, still 5 kilohertz, 2 kilohertz and 1.5, it is for the 5 kilohertz, and it is for 1.5, sorry 2 kilohertz, and it is for 1.5. Okay, for the last part write the three samples. It is at 1 kilohertz and 3 kilohertz. So for this also just complete this experiment and submit it through the course method.